Ah, good. We're now streaming live. I love the Hubble deep field image. It's one of my very favorites.
Mesmerizing.
Any word on whether or not they've gotten the computer to reboot on Hubble?
I have not checked.
I've not heard anything. It stuns me that the whole computer module is a 1980 processor.
Yeah.
And they went up there in what, about 2000 or thereabouts? And
2009, I think they put a new
2009. I'm like,
computer up there.
why did you guys replace it with at least a 286 or if not a modern i7 processor.
No quick fix for Hubble Space Telescope's computer glitch. That was 7 hours ago.
Okay, well.
Both the primary and backup computer are experiencing the same error.
And that error is they're ancient. How many computing generations is that between 1980 and now? 1980, we were still selling the Apple IIe, right? The little Osborne.
What about, but we're built in the 1980s. Okay, so even the one that's up there, they got installed in 2009, was built in the 1980s.
Right. And they tested it before they launched it, but still.
Well, no.
Yeah.
They're pretty ruggedized, so.
I'm sure they are.
Yeah.
I'm sure they are. Do you remember the Osborne transportable?
I don't remember it, but I remember the Osborne company.
Oh, yes. Osborne had the first portable computer. It was the size of a fairly large, I don't know if it would fit in an overnight overhead bag. It was that big. It was huge. Weighed about 40 pounds. You set it down on the table like a suitcase, and the end folded down for a keyboard. It had a little 5-inch CRT screen flanked by two 5 1/4 floppy disks. That's 1980 computing power, boys. Oof. CPM processor.
Yes.
Yeah, running at about 0.5 megahertz. Astonishing.
As long as it runs.
Yeah. Well, I sold that stuff. I was selling computers back then. And worked my way through college. Sold Apple II Plus and Heathkit and Commodore 64s and the Osborne transportable. And the first hard drive I ever sold was a Zenith Heath 5 megabyte hard drive that was 30 inches long, almost 15 inches wide, 10 inches tall, weighed almost 40 pounds, needed a power supply the size literally of a brick.
Right.
And when we sold it to people, we said, oh, the company line was, you'll never fill this much storage.
You'll
And
never, yeah, it would be impossible.
yeah, it would be impossible to fill this. And it was and it cost $5,000.
I'm Connor Nixon. I'm a planetary scientist at NASA's Goddard Space Flight Center. I study the atmospheric composition of the outer planets. Titan is Saturn's largest moon. It's actually the second largest moon in the solar system. And it's the only moon in the solar system that has a large and substantial atmosphere. And that atmosphere in some respects is really similar to that of the Earth, being composed mainly of nitrogen, but in other respects it's really different. It has methane as its second most abundant gas, and that takes the same role as water vapor in the Earth's atmosphere. It evaporates from the surface, it forms clouds, and then rains down again, and in fact forms lakes that we see at Titan's North Pole, including ethane and propane and all sorts of complex chemicals. We also see these vast dune fields at the equator, which are not made of silicates as they are on the Earth, but actually made of organic substances, essentially plastics, which have actually sedimented from the atmosphere and are being blown around into dune fields, the same as we'd see on a desert on the Earth.
I want to go.
Mike Wiesner says, I still
Back
have
in
my
1980, when
Apple
Voyager 1 flew by
1980
Titan and made the first close
Apple
encounter
II
with
Plus.
that moon, it discovered many new chemical species in the atmosphere. And a lot of these are what we call hydrocarbons, which are composed of two types of
Carol
atoms,
Black says, "Good
carbon
afternoon,
and hydrogen.
fellow
And these are
photon
derived from
gatherers."
methane. After the
Yes.
methane is broken apart by sunlight, it forms into longer and longer
Brian
chain
Fanning
molecules.
says, hello
so you can
from
add
North
first
Wildwood,
two
New
carbons
Jersey.
together to make a family of molecules. And you can also form three carbons together to form a heavier family of molecules. So it was actually very mysterious that Voyager only discovered the heaviest and lightest members of the three carbon family, but it didn't find the middle member of the family, propylene, that was missing. So NASA has this wonderful flagship spacecraft called Cassini, which is currently orbiting Saturn and is making multiple close flybys of Titan. Now in visible light, Titan appears quite bland and featureless, just like an orange globe, but Cassini has techniques to peer through that haze, including the composite infrared spectrometer, or Ceres, which can look at the heat coming from the atmosphere and split it apart into its different frequencies, and this forms a characteristic pattern of peaks, which give the characteristic signatures of different molecules. And through this we can detect which molecules are in the atmosphere. We see all the molecules that were previously discovered by Voyager. But we're also able to look for new molecules, and in fact, buried within the signatures of these more abundant molecular species, we saw a very small spike, which was due to a new species which had not been seen before. And in fact, this was propylene. We saw it at multiple altitudes in Titan's atmosphere. When we added all the signal together, we had more than 99% confidence that we were discovering a new molecule. So this object I have right here, this is polypropylene. This is a plastic we use on the Earth in everyday household objects, such as this plastic tub here. And if we turn it over on the bottom, we find a symbol, the number 5, that says PP, polypropylene. This is the propylene that we found on Titan, but polymerized. That means that the molecule is formed into long chains, and when these chains are tangled together, it forms a hard, clear plastic that we use in many household objects. So that was really fun for me to realize that something that we discovered in space was in fact something that I was touching every day on the Earth. So the discovery of propylene on Titan is really exciting. First of all, it completes this chemical family where we had this missing link dating 32 years back to Voyager. But also it shows that there's much more there still in Titan's atmosphere to be discovered. Some people think that Titan is similar to the prebiotic Earth long ago, when the molecules were forming the basis of life. And we don't know what we're going to find on Titan if we send back further spacecraft with new instruments, more sensitive instruments, if some of the molecules on Titan could be similar to the basis of life on Earth.
Well, hello, everybody. This is Scott Roberts. And of course, I am here with Dr. Daniel Barth on the 15th How Do You Know program. And this is all about classification and naming of, or I guess, classifications of these things called moons. So, back in, the early part of the 2000s, I actually was looking at it as like, I think it was 2006, maybe 2009. The IAU had demoted Pluto from a planet, the ninth planet, down to a dwarf planet, and so that was done for various reasons. They had their descriptors for it, but occasionally these things get revised, and I think a lot of it's cultural, as well as scientific. So, there's certainly, in the case of Pluto, there was an overwhelming amount of people from the public that did not want to see this demotion. And there's quite a few planetary scientists that didn't want it either. So there's still controversy over that particular classification. How about the moons, Daniel? Is it similar in the moon world?
It is. As we talked last week, Scott, I showed you this large pile of textbooks from my library behind me here. I've taught or used, 15, 20 different reference books over 40 years of teaching astronomy. And it tweaked my interest, and I went back and I looked through. All but one of them failed to define the term moon. And this comes back to the idea that astronomy is truly the most ancient science. We have Stonehenge and other henges around the world, these stone monuments erected to be used as calendars and astronomical computers, really, for the turn of the seasons, because for early primitive man, agriculture was survival. And without a good calendar, plant now, harvest then, people die. And the stone structures we know now, most of them were predated by wooden structures that were there for centuries, and then they erected the stone structures. So henges date back 5,000 or 6,000 years. Clay tablets with familiar constellations, Scorpio, Capricorn, things like that are on the ecliptic, the zodiac constellations. We have clay tablets, radiocarbon dated back 15,000 years, 15 millennia. So we're talking 13 millennia before Christ. That's a time scale that's really hard to grasp. We have lunar phase calendars in a figure 8 that are carved on antler bone, dating to well over 50,000, between 50 and 80,000 years. So astronomy is the most ancient science. I'll just put it out there. If anybody thinks there's a more ancient science, I'm up for a discussion, but I'll just put it out there. It's certainly, if not the oldest, it is one of the oldest. Because of this, astronomy carries this tradition of the millennia. Science changes rapidly, especially in the modern era, but if you consider 80,000 years of astronomy, the last 4 centuries is an eye blink.
Yes.
And so science can change very rapidly, and one of the consequences, as with the term planet, we have these ancient colloquial terms that used to mean one thing culturally, a noun usually, naming a thing there in the sky. It's a bird, it's a plane, oh, it's the moon. And yet now science vocabulary is quite specific. And unlike so much of language today seems to be experiencing a fluidity, the language of science does not. If you say heat or energy or work or motion, velocity, these things in science mean something very precise. And we keep that precision so we can communicate across language barriers, cultural barriers, and we can communicate in the language of science and mathematics. And this is the only way we have a world community of scientists. Moon is one of these, it's like your appendix. And well, I had mine out. You can't do that to the moon. But this idea that the term moon has come to mean different things. And my astronomy texts did not define it. And I'm looking at 1, 2, 3, I went through 15 books, nothing. I finally came across one of the most recent reference texts I used from 2012 or thereabout, and it did have a definition for moon. So just interestingly, I went and looked at some dictionaries. I went online and give me the top 20 dictionaries, Google, and so it gave me the top 20 dictionary sites. Believe it or not, only about half of them define the term moon. A lot of them do not. I will not give you the Urban Dictionary for moon. That's rather rude, but we'll just leave it at that. But for a lot of these, the errors are stunning. Moon, that's the only M-O-O-N, moon. Natural satellite of the Earth, visible chiefly at night. We know that's not true. Half the month, the moon's visible in the morning sky.
It's true.
And visible chiefly at night by reflected light from the sun. That's Bing and Google. And it's not true. Well, it certainly has errors. And the fundamental error there is it says the idea of moon, there is only one. Everything else is not a moon. Right? So if you say Cincinnati is this city in Ohio, well, what about other cities named Cincinnati? What's the most common city name in the United States? I think it's Springfield. Well, if you look at Springfield and say, oh, it's the one in Illinois where Lincoln was first elected senator. Okay, what about all the other Springfields? What about the one we have here in Missouri? Quite a nice town. Is it not a Springfield? So I have a problem with these definitions that say, oh, it's Earth's moon. Some of them get really specific. It's a natural satellite at a mean distance of 238,857 miles, having a diameter of 2,160 miles. So as the orbit expands, is it no longer the moon? You get these odd things where people are saying, oh, it's that one. That's the only thing. And secondly, they're confusing temporary attributes with essential and permanent attributes. The Earth's only natural satellite, Wikipedia, that's wrong. The Earth has a number of natural satellites. The Earth's only permanent natural satellite, that's Wiktionary, that's wrong. We discussed this in our previous How Do You Know program. There are no permanent satellites.
There's no permanent moons, right?
There are no permanent moons. They are not permanent.
There's no permanent anything, I suppose.
And it's the height of I suppose, cultural bias to say, well, it's been here for all the time. People have been here. It must be forever. Well, sorry, astronomers take longer time scales than that. The most fun one, what someone wants to give you when they wish to give you everything. That's the moon. That's in yourdictionary.com.
That's true.
And I like this one. This is from Collins Dictionary. The moon is the object you can often see in the sky at night. I think that would apply to the Starlink satellites, wouldn't it? Yeah. And you look at these and you're stunned and you're thinking, oh, this is the internet.
Maybe think about this a little deeper than that, you know?
Yeah. Wouldn't you find something? And then I went through all these books and it's amazing. Amazing. And very well-known authors, James Fix, Abel, who did Exploration of the Universe, Kaufman, Chasen and Macmillan, who've done the most popular series of astronomy textbooks in the nation. They don't define it. Seeds, Smith, Bachman, they don't define it. They're just like, nope, we're not. Sorry,
can't.
Not stepping in that mud puddle. Not doing that. So the one good definition that I found was pretty reasonable is in the text "Understanding Our Universe" by Palin et al., and that was published in 2012. It says a less massive satellite orbiting a more massive object, which doesn't distinguish between artificial and natural. And it says moons are found around planets, dwarf planets, asteroids, and Kuiper Belt objects. Okay. Still doesn't mention exoplanets, still doesn't mention rogue planets, which I am assuming that I'm certain, statistically certain that those have moons. But it gets closer because if you're a moon, it's really a relationship. Moon is a term like sister, brother, uncle, cousin, mother. If you're someone's sister, it's not because of just who you are, it's your relationship to someone else. Moon really defines a relationship to a larger body. So I want to take some time today and see if we can define this idea of moon. Now, when we talk about inherent and temporary qualities, something that's inherent is essential. For instance, let's talk about a rock. I don't have one handy here, but you know, I've often brought my pet rocks from around my garden into the studio. A rock is something, what is a rock? If we define it, well, it's an aggregate of minerals. It's chemically bonded into a coherent crystalline solid. And these are essential qualities that define what it is to be a rock. Now, we can have all sorts of qualities. We can have things like color, temperature, location. You can be a seafloor rock. You could be a mountaintop rock. You could be a red rock. You could be a blue rock. One rock, two rock, red rock, blue rock. Apologies to Dr. Seuss, Theodore Geisel. But all of those rocks, wherever they may be, share the essential qualities of being an aggregate of minerals, crystalline solid, atomically bonded together. And one of the interesting non-essential or temporary qualities is motion. When we talk about dwarf planet, the third and most controversial attribute that makes a planet into a dwarf planet is a state of motion. You must be in orbit, and the definition says in orbit around the sun. Other exoplanets need not apply. That seems rather, let's leave that one aside. But it says that it gravitationally dominates and clears its orbit, which gives you the idea that a young planet in a crowded and dusty solar system on some one fine day bumps the last,
Right.
asteroid out of the way, and a little flag pops up that says, "Planet,
You are now a planet."
you are now a planet." It's like a video game. Welcome to the next level. On this basis alone, I reject this definition.
Right.
Say that, is it not a car if it's parked in your driveway? Is it only a car when it's in motion on a road or a highway? Does it have to reach a certain miles per hour to become a car? And before that, it's just this other thing, dwarf car, stationary
It has
car.
to be able to clear its highway of traffic.
Oh, I see way too many people in California driving that way. And out here in Arkansas too. Let's not fool.
Yeah.
California has no monopoly on crazy drivers. So this is this kind of thing. I think we need to stick to essential qualities. The other thing, Scott, that on this program, many times we go back and we talk about, let's talk about the giants of our field of astronomy. And we're going to go back to Aristotle. Aristotle, and for all we have, thumbed our nose at him as a discipline for the last 5 centuries, Aristotle is a giant of our field. And Aristotle had this bias that all orbits must be perfectly circular. And this perfect circle bias was something that is so mathematically pure and beautiful. And of course, because it's beautiful, it must be true. Kepler struggled for 20 years trying to fit the observations of Tycho Brahe of the planet Mars into a circular orbit. It didn't work.
Oh,
It didn't work. He spent 20 years. Well, rip out that page, try it again, go from scratch. And he had this idea, because I'm rejecting Aristotle's perfect circles, I'm wrong. Of course, Kepler eventually discovered beautifully that orbits are elliptical. The central body, be it a star, be it a planet, is just one focal point. The other focal point is empty out in space. Orbits A circle is just one out of an infinity of possible orbits. And when you're talking about the odds of one out of infinity, and of course, circle is a very narrow definition. If it gets bumped, if it gets disturbed, it wobbles back into an ellipse again. So circles are what Aristotle himself would call an improbable possible. Something that certainly is possible, but it's not likely. Well, Copernicus predates Kepler. And we have something in science today we call the Copernican Principle. You're familiar with it, I'm sure. The mindset before Copernicus, the Earth is the center of the cosmos. I'll just use the generic term cosmos. What they were talking about, we would recognize as solar system, but they really meant the whole shebang, right? The entire
universe.
The entire universe, although they didn't use that term at all. Well, Copernicus said, in essence, the Copernican Principle, and he doesn't actually say this. I have a copy of De Revolutionibus on my library shelves here. He doesn't actually say this. He doesn't actually say, well, if you think your location is special, you're wrong. But Copernicus took the Earth out of its special position, and people liked it because it was theologically significant to them. Heaven is up beyond the shell of the stars, and hell is down below our feet. And we people are in the middle, and the Earth is in the center because God favors us, and on and on. It was a theological argument more than a cosmological one. Galileo warned the Pope about this. Don't set principles of science to be theological principles because science changes. Faith and theological ideas are supposed to be more eternal than that. Okay, fine. Copernicus took the Earth out of the center. And then he said, we're just one of a number of planets. In that case, in his day, 6. And he said, not only that, our star is only one among myriad stars. And although he never says this, he never crosses this line, the multiplicity of worlds. Giordano Bruno, 1600, a disciple of Copernicus and his work, is burned at the stake for heresy, for daring to say there is a multiplicity of worlds. We are not God's only creation, special in heaven. And all those other stars are other solar systems.
Wow, he was burned at the stake?
He was burned at the stake in 1600, April 1600.
Holy smokes.
Yeah.
Literally.
They offered him the chance to back down. He wouldn't. There's a man of principle.
There's a man of principle. It's getting hot in here. It's getting hot.
Yeah, and a horrific death. Copernicus himself studied in Padua, Italy, and some historians claim that Copernicus would have likely seen one or more executions by burning, which is why he kept everything so close. He only took on one student, Joachim Rheticus, a German Protestant who heard about his work and was searching through monasteries in Poland to find him. And he took the manuscript back to Germany, got it published because you couldn't get it published in Italy because Inquisition. And
that little inconvenience called the Inquisition.
Correct. Everyone's afraid of the Spanish Inquisition. Terrible line from a bad movie, but true. So Copernicus not only takes the Earth out of the center, he takes a star, our sun's position, as the lamp unto the darkness. He takes all of this away and says, you're not special. As a teacher, you get in trouble saying that.
Yes.
I'm just putting it out there. Although it's true, I'm not special. Scott's not special.
No.
The Copernican Principle says, you know what, folks? And Copernican Principle has been basically extended over 500 years. If you're looking at a theory and it requires something to be special, unique in nature, there's likely a gigantic flaw in your theory. It's become a founding principle like Occam's razor. Occam's razor says the simplest solution is most often true. When you hear hoof prints, you think of horses, not zebras, unless you're in, the savannah in Southern Africa, and maybe then you think of zebras, not horses. But generally, the simplest solution is almost always true. Science, for all its complexity, the solutions we have are the simplest ones there are. You take the flat Earth, which is wildly complicated and acknowledges some points and puts blinders on, plays the see no evil game with others in order to maintain. And we take a look at modern ideas of science and astronomy and Hubble's island universes. Galaxies are island universes. You know what? It's the simplest situation that fits the facts. Well, we look at these Copernican principle and we say, so circular orbits don't make it, they're elliptical. You know what? If you think all orbits have to be Keplerian ellipses, that's just another version of the Copernican fallacy. Oh, it has to be an orbit like this. No, it doesn't. No, it doesn't. That's silly. Why are elliptical orbits special? Do you remember the argument that Pluto isn't a planet because it's tipped 17 degrees?
Yeah.
And the Kepler satellite found planets which are orbiting tipped 50, 60, 70 degrees to the rotational plane of their star.
Maybe it wasn't tipped far enough.
Right. Well, big planets like Jupiter and Saturn tend to wander over the eons, and they play merry hell with orbits. They take things and crack the whip and fling things into different orbits. Sometimes stars capture rogue planets, and those can be from anywhere.
Right.
And so this idea of, oh, it's not a circle, it's an ellipse. Oh, and it has to be within so many degrees of the plane of the ecliptic, or it's no good. Every time we've foolishly violated the Copernican principle, we've been wrong. Hubris, hubris, hubris. And this is ultimately the stumbling block upon which the IAU's faulty definition of planet will trip and stumble and crumble away. It assumes, oh, planet is special. Planet clears its gravitational path. Sorry, Copernican principle? Yeah. Copernicus, Nick's going to get you. So
Right.
we come back to the idea of moon. So if we're saying, well, moon is a relationship between a big body and a smaller one, if we're not going to go with elliptical orbit, how do we define this? Well, I think we can do this quite nicely. And again, I'm going to share the screen and show everybody a lovely image here. I didn't do this one, guys. You can probably recognize the quality graphics. Oh, Dr. Barth didn't do that one. No, he did not. But I did do this one. What I did, I'm hoping you can see it. I took a piece of clay and I smushed it into a flat surface, and I took a pizza cutter and I carved grid lines on it. Well, if we take this and we punch it into the center and we make it, oh, here we go. There we go. It's now not flat. Space-time is not flat. And we can see here, Scott, that we've got a planetary body distorting space-time. This is Einstein.
Okay.
Space-time, John Wheeler said it best. Mass tells space-time how to curve. Space-time tells mass how to move. Journey into Space-Time and Gravitation, John Wheeler, Scientific American Books, wonderful resource. Well, we look at this and we see we have this gravitational well. My idea, Scott, is that a moon is any object, a natural object confined within the gravitational field of another more massive object. It's a simple idea.
I'd say that.
Go ahead.
I said that I would say that cuts it for sure.
Yeah.
Yeah. Now I've also, there's moons and there's moonlets, right? I guess the
Correct.
moonlets are not round.
Correct. And again, we can take an idea. So let's go ahead and put up our moon definition here.
Okay.
And again, I'm going to make this a little bigger. Whoops, not that big. So everybody can see it. And we've got our screen there. Moon, an object large enough, 2 points here. And we're actually following the IRU to a point. An object large enough to compress itself into a spherical shape. The IAU goes into a lot of things. They say a planet is not a perfect sphere. It's in hydrodynamic equilibrium, and otherwise, when it spins, centrifugal forces make it bulge at the equator, but it's as spherical as it can be in its rotational state. So we're just going to simplify the language. An object large enough to compress itself into a spherical shape that is constrained within the gravitational field of a planet. So if you're constrained within the gravitational field of a star, you can say, oh, that's a planet. An object large enough to compress itself into a spherical shape confined within the gravitational field of a star. Doesn't specify the angle of your orbit or its shape.
Right.
But the second thing about a moon's motion is controlled by the planet's gravitational field as it accompanies that planet around its star. So we have two things. One, there's a relationship between the planet's gravitational field and a second object. That object is big enough to compress itself into a sphere, and the Earth's motion and gravitational field unite to control the motion of that moon as it accompanies the planet around the star. Note that this definition says nothing about a particular kind of orbit. Like, as Kepler rejected the perfect circle as necessary, I reject the Keplerian ellipse as necessary. Why do I do that? Well, it turns out that if you have a big object, like our moon, like a captured object like Phobos or Deimos around Mars, 10, 20 miles wide, if you have a really big object like that, then the orbits are almost always elliptical, Keplerian ellipses. As we know, they're not stable. They're either shrinking or contracting, Roche effect. But when you have really small objects, it's not necessary for them to have nice elliptical orbits. We can get into some much, much more interesting shapes. So if we take a look at this idea, we realize we've had the clues to this mystery all along. And I'm not sure when Trojan asteroids were discovered, sometime in the mid-1800s, I think. But we realized, and they were named after, I think, Ajax and Achilles, right? The two heroes of the Trojan War.
Sure.
One at each point, and then we realized, it's a whole family. And actually, it was sometime in the late 1700s. Joseph Louis Lagrange. And you look him up, Scott, there's at least half a dozen different spellings of his name. Why, I'm not sure. But
Lagrange, mathematician, right?
Right, mathematician and astronomer. And he was studying the gravitation between two bodies. And he stumbled upon the happy idea one day. He said, wait, wouldn't there be some point between the Earth and the moon where the gravitational field balanced itself? And what's very interesting, if you talk about astronomy and space travel in popular culture and media, the movie Frau im Mond, Woman in the Moon, Fritz Lang, 1926, really brilliant piece of futurism. He has 3-stage rockets. He has retro rockets to go into orbit around the moon, and landing rockets and all sorts of cool stuff. But one of the things he got wrong, and his consultant was Hans Bethe, who was a German Nobel Prize winner, is he shows this diagram and he says, there is one point between the Earth and the moon where weightlessness occurs. And in the movie, they have the rockets firing all the way out and all the way back. And of course, as we know, I forget who did the famous line. I think it might have been Michael Collins in Apollo 11. And they asked him, well, you're between the Earth and the moon. Who's driving? And he laughed and he said, I think Isaac Newton's driving right now.
Yeah.
And they were, of course, on a free fall path. They basically used their rockets to set them in motion on a free fall path that would take them to the moon. But Lagrange comes up with this idea in the 1760s or 70s that there is one point between the Earth and the moon where the gravitational fields balance. And he said, you know what? If you had an object there, it would just hang there. It would orbit around the Earth. It would be dragged around in a slower orbit. Its speed would be retarded. Normally, we think of things take longer to orbit the farther away they get. That's Kepler as well, laws of planetary motion. And he said, well, although this should be orbiting faster, it isn't, because it would be held back because it's in a gravity well. And what we mean by a gravity well, Scott, think about a marble on a tabletop.
Sure.
Well, if you have a marble on a tabletop, you could bump it and it would roll off and hit the floor. But if you have a marble in a bowl, I can disturb my little marble here a little bit and it comes back because it's in a bowl. It's in a gravity well.
Mm-hmm.
We can't see it, but we can measure it. We can observe it by its effects on things. And L1 is just one of 5 Lagrange points. And if we look at this idea of different Lagrange points, I'm switching to a new diagram. There we are. This again, I was going to draw my own, but this is from NASA. And it's illustrating L1, 2, 3, 4, and 5. L1 is easy to understand because the attraction between the Earth and the moon balance. L2, however, there's a point where the pole of the Earth and moon combined counteract the centrifugal force that would normally send a satellite there flying off into space. We have a number of observatories lurking there. And the next one to go up is the James Webb Telescope, which will be
at L2, right?
Right. About 1.5 million kilometers beyond the orbit of the moon. And it will sit there, and obviously it's well beyond the radiation envelope of Earth. It's well beyond the reach of any space debris. It always has the moon between it and the Earth, so it's not getting either thermal or electromagnetic radiation to disturb it. It's a wonderful place for an observatory. L3 is the least stable. And that's where the pole, that's basically a point exactly opposite the Earth in orbit. This was, again, something popular in science fiction during the late 1800s, early to mid 1900s. There was a secret planet that orbits in our orbit that's opposite the sun. We can never see it because the sun is always in the way, which is theoretically possible, but the gravity well at L3 is really, really weak. It's very far from Earth. And so that little gravity well there is really, really tiny and insignificant. I don't know of any satellite of any planet that exists in an L3 point. L1 and L2 satellites are relatively common. L4 and L5 were actually the first 2 that were discovered, and that's the orbit of Jupiter, and those points are 60 degrees ahead and behind. And we could do the math, but we're not gonna. If you download, folks, the illustrated guide to today's program, the links to the math are there, and I encourage you to explore. But L4 and L5 are basically 60 degrees ahead or behind the planet. There's a nice gravitational well there. Obviously, the bigger the planet, the bigger the well. Well, it turns out that the Earth has satellites at L4 and L5. Moons, in fact. They're not very big. I mean, if they were coming towards the Earth, they were going to hit somewhere, yeah, they'd be considered big. They're about 350 meters across. Those are the ones we've seen. There are likely others. We thought there were only 2 Trojan satellites around Jupiter. We know now there's a whole family. But you know what? This point, 60 degrees away, is a many, many millions, tens of millions of kilometers away from the Earth. Asteroids, as you know, are about as the color is light reflectivity is comparable to fresh blacktop. They're not very reflective. And if you're talking smaller than 350 meters from that distance, they're almost impossible to image. And they're moving really slowly. And you know what else? It and Earth move around Earth's orbit together. So they're really difficult to image against the star field because they're really not moving very much because we're moving against the star field the same way they are. So they're really difficult to image. I suspect there are more, but we don't know that yet. But we know for a fact Earth has one in each L4 and L5. Well, the interesting thing is that the orbit of these things is not Keplerian at all. Not an ellipse. And if you go into this idea, you get this really weird orbit. And in fact, these objects describe kind of a horseshoe-shaped orbit, which we know there are moons around Saturn and Jupiter which do this. And Hyperion is one. And they have these orbits which are essentially horseshoe-shaped, and they don't complete a complete orbit around the sun. But you go back to the definition of moon we put up earlier. Is it confined within the gravitational well of the Earth? Yes. Does the Earth's gravitation control it as it circles the sun? Yes. And we're throwing out, because Copernican Principle, we're throwing out this bias. An elliptical orbit is necessary. No, it's not. No, it's not. So we're letting Einstein drive. We're saying, all right, how do we define moon? Yeah, it's confined within Earth's gravitational field, and Earth's gravitational field drags it around the sun, and it accompanies us on our orbit. And in fact, these objects do. And Lagrangian moons, if you want to add a prefix, certainly, you know, I'm not going to say a Lagrangian moon is not a moon. Quite the opposite, a Lagrangian moon is a moon. It's just a temporary attribute. It is not a permanent attribute. It is in a gravitational relationship with the Earth. The Earth is the dominant partner. The Earth controls its orbital motion. The Earth controls its orbit around the sun. It's a moon.
Right, but not for forever.
Not for forever. Then we get into the idea of moon versus moonlit. And here I'm going to give a little nod to the IAU. I don't think they're wrong when they split planets and asteroids. And the essential difference, Scott, do you know what it is? Sure you do.
Doesn't orbit a planet, right?
It's not round. It's not a sphere.
Oh, it's not round, but could it be a moonlet?
Well, an asteroid can occupy an independent orbit around a star. You know, well, why isn't it a planet? Planets are large enough to compress themselves.
Right, round. Yeah.
If it's shaped like this, if it's round, it's a planet. You know, if it's kind of, you know, shaped like this.
I would say if it's round, has geology, and is orbiting its parent star.
Well, if it's large enough to compress itself into a sphere, and there are a couple, Ceres and Vesta are two that are just on the cusp. Vesta is not considered a planet, not by anyone. Ceres, we give it the label dwarf planet, and I'll accept that adjective, but it's still a planet. If you want to say rocky planet, you know, terrestrial, gaseous, ice giant planet, fine, all are planets. Old bald guy, still a guy. So we get this adjective issue out of the way, but when we get this idea of, oh, an asteroid, yeah, and a lot of them are shaped rather like this, and you can clearly see that there's kind of a waist between them. This looks like kind of the asteroid that we had the recent mission that it landed on, right? Grab some samples. And the name of the asteroid is slipping my mind. Somebody in the chat will probably tell us. But basically, it looked kind of like this. It looked like, oh, two things stuck together. Yeah, sure. But when things get large enough, and it's not a flying rubble pile anymore. NASA has lots of planetologists and astrophysicists adopted the popular descriptor, a flying rubble pile. A lot of asteroids are not cohesive objects. They're simply a pile of rubble held together by their own comutual gravitation. When you get large enough, Ceres is large enough. Ceres is a true sphere. Its own gravity has crushed it, changed its geology, and changed its morphology. If you look at Ceres and Vesta, Vesta is kind of like this diamond. It has this weird line of mountains around its equator. And you could see it's not spherical yet, but Ceres is bigger. It's about 960 kilometers, and it's big enough, it's crushed itself into a ball. If it's big enough to crush itself into a ball, the internal pressure is great enough to start forming cohesively bonded materials. Remember rock? A cohesively bonded set of minerals held together in a crystalline solid by atomic bonds. When you get big enough to smush yourself into a ball, you get big enough to change your geology. That's a planet.
That's a planet.
Ceres is a planet. Pluto is a planet. Okay.
What about these rogue planets that I hear about?
Well, rogue planets, and again, we get into the Copernican Principle. Do planets indeed have to have a permanent relationship with their star? Rogue planets have been ejected. I'm sure Jupiter and Saturn in their migration in and out probably ejected a few, bullied a few neighbors out of the neighborhood. Off you go. And some studies indicate there may be as many as 1 trillion rogue planets.
1 trillion?
1 trillion in our galaxy.
Wow.
An observatory in Australia went looking for rogue planets, and they were like, wow, there's a lot of them. And they were looking at one-time extinction events from the light curve of a star, and they're like, wow, there's a lot of these.
I see.
And they estimated there may be 1 trillion. Well, if you think about if an average planetary system starts out with 30 planets and ends up with 10, there's a lot of evicted neighbors out there wandering in the cold and dark. Some may still be geologically active. I'm imagining many have frozen and died, become geologically dead. But it's an interesting idea, the rogue planets. Do they have moons? Yeah, I'm sure they do. Some of them. And so if a planet is defined as something, it's defined as a relationship, like we've defined moon. An object large enough to compress itself into a sphere that orbits a star, that incorporates our planet, it incorporates exoplanet. And interestingly, it does not rely on a particular gravitational pinball event. Oh, I've nudged the last asteroid out of my orbit. It doesn't rely on anything like that to achieve planethood. It's simply its own gravitation and geology. Now, when can you classify something as a planet? You've got to be able to image it sufficiently well to say, yeah, that's round. When James Christie discovered Charon, the moon of Pluto, they didn't have sufficiently good imaging at that time to say Pluto was round. They really did not. Not until the Hubble era did we have sufficiently good imaging. And even in the Hubble era, it was dubious whether or not Pluto was round. And okay, now we've had New Horizons. It's flown by. Pluto is absolutely a sphere. And if you can find the diameter, if you're more than 1,000 kilometers, we don't know of any material that could withstand spheration, gravitational compression into a sphere beyond a radius of 1,000 kilometers. An icy moon would compress at a smaller diameter than a rocky silicate moon would compress at a smaller diameter than a metallic body. But at some point, it doesn't matter what you're made of, gravitation is mighty and will compress you into a sphere. Generally, I think if you can see something and say, yeah, it's bigger than 1,000 kilometers, it's a planet. The gravitational processes are going to be overwhelming, compress it into a sphere. Just like planets, so go moons. If they're large enough to be spherical, they're a moon. If they're too small to do that, if they're potato-shaped, moonlit. And yes, I'm putting forward this term. And let's take a look at my definition for moonlit. And I'll share the screen here. And again, very similar to what we had before. An object constrained within the gravitational field of a planet, but is too small to compress itself into a spherical shape by virtue of its own gravity. Like a moon, a moonless motion is controlled by the planet's gravitational field as it accompanies that planet around its star. So, Lagrange points. Could you have a Lagrangian moon? Jupiter might be big enough. Certainly some super Jupiters might be big enough to capture something as big as Ceres, 1,000-kilometer threshold. That would be a true Lagrangian moon. I don't think that any of the Lagrangian point objects in our solar system is an actual moon. I believe they're all Lagrangian moonlets because they're not spherical yet. So moon and moonlit. And so we get this idea, wow, okay, so we've got a moon, we've got a moonlit. What's the difference? Gravitation, the gravitational process of compressing an object into a sphere, which must happen. Nothing can resist it. No material can resist it. And it's in a relationship with a planet, a very specific relationship. It's confined to the planet's gravitational field, and it accompanies that planet on its journey around the sun. It does not specify a shape of orbit. The Copernican Principle tells us, don't get too particular that you think some special circumstance has to occur. That's nonsense. It doesn't work. It's not functional. So moonlit, Phobos and Deimos, which have been called the moons of Mars since they were discovered, actually moonlets. Neither of them are a sphere. They're like 9 and 22 kilometers, something like that. They're very small. They are not captured asteroids, almost certainly not. But moonlets, yes. Jupiter and Saturn. Jupiter has something like 70 confirmed satellites, Saturn 65, and the numbers keep going up. Not all of them are moons. Many of them, most of them are moonlets. And we know Jupiter has a series of retrograde satellites. It has satellites tilted at different attitudes. It has satellites like Hyperion, which have Hyperion has a chaotic spin axis because it's always it's being bumped by its neighboring moons all the time. So it's not stable. But all of these are moonlets. They fit the moon definition, not by virtue of the shape of their orbit, but by virtue of their relationship with a planet as it orbits a star. Now, if you want to say a planet is defined by its relationship with a star, I suppose we need a different definition for these rogue objects. Maybe we just call them rogues, rogue worlds. They could have moons. They could have an object confined within their gravitational field, accompanying them as they travel through the interstellar vastness of space. But the idea of moon is indisputably a relationship. So moon, like uncle, brother, sister, mother, father, cousin, it's a relationship between a planet and an object confined to its gravitational well. So we have this idea, and I'm going to throw one more at everybody, because I'm sure a lot of our listeners, Scott, know that originally when news broke of the Sputnik satellite, late 1950s, right? And
yes,
the New York Times headline, which was very famous, Soviets put baby moon into orbit.
Yeah.
Remember that headline? It's very famous. Well, If that was a baby moon, and virtually no one uses that terminology now. They say, oh no, Sputnik was a satellite. Hubble is a satellite. We have weather satellites. We have communication. We have Starlink satellites. So I'm going to go ahead and make it official. Satellite is an artificial man-made object that is constrained within the gravitational field of the planet. I'm supposed the science fiction minded among us might say, hey, Dr. Barth, you're doing the Copernican fallacy again. Get rid of man-made. Other species could have made their own around their own planets. Yes, that's true. Unlike Moon or Moonlit, a satellite's motion may be controlled by the gravitational field of virtually any object. We've put satellites in orbit around asteroids. We've had satellites intercept comets. But unlike moons, the motion of satellites are planned and controlled for the purpose of gathering scientific data. The motion of satellites is not random. It's scientific. It's controlled by the hand of man. And sometimes we do this well, sometimes poorly, but nevertheless, it's under our control. It's an artificial thing that's put in a particular place for our own purposes and controlled by us. It's not necessarily controlled by its relationship to the gravitational field of a body. We've sent satellites to land on asteroids and then fly away from those and return samples. We've flown satellites in the path of comets and have them come back to Earth to return samples. So their satellites aren't controlled by the gravitational field of one object. We've had satellites that we've launched from Earth and put into the gravitational field of the moon where they remain. So satellites are an artificial thing controlled by people for their own purposes, and that makes them different. And this really puts satellite into the sense in which we use it in modern language. We very rarely talk about moons and moonlets as satellites. Sometimes you see people do it in a David Attenborough kind of almost sophisticated science communicator sort of way. The satellites of Jupiter. Yes, we do say those sorts of things occasionally, but in fact, in parlance, both scientific and casual, when you say to someone, oh, did you hear about the new satellite? They are not going to be thinking about a rock in space.
No.
They're going to be thinking about something people
that
made,
we built.
people put there, and oh, really? What's it for? What new fascinating science is it going to do? Who's it spying on? Oh my God, they're ruining the view with my telescope. They're going to be talking about man-made objects for good or for ill. So I'm just putting it out there, friends. We now have 3 new definitions that are precise.
So I'll throw something out there. Is the International Space Station a satellite?
Certainly.
There we go.
Artificial object. It was put in place by people. It's motion. And we move it. When we think it's in danger of collision, we move it. We're able to move it.
Good.
Yeah, because collisions in space are bad.
They're bad.
They're bad, yeah. I don't know if, let me see. Yeah, here we go. Here's a, on my table of junk from my workspace that you get to see the nice, neat, organized part.
Yeah.
This is a order 20 bolt with a half a dozen washers and a nut on it. This is about, 75, 80 grams. At orbital speed, Scott, this impacts with the energy of a U.S. Marine Corps hand grenade.
Yikes.
Yeah. And you know what? Doesn't matter if it's a blob of liquid or solid. It doesn't matter if it's one thing or just a flying rubble pile. That's unlikely in Earth orbit, but let's just go with it. This has terrific impact energy. And something like this, there have been impacts on the space station. NASA looks and occasionally plugs leaks. The space shuttle famously came back one time with a hole through one of the horizontal tail pieces, a hole the size of a beer can.
Whoa.
Punched through. And they didn't find it until they landed. Like, whoa, what's this?
Yeah, big hole here.
Big hole, yeah. So in terms of the space station, something this size would be devastating. This
Yes.
is a half-kilogram ball of clay, 500-gram object. The kinetic energy, because the orbital speed is what, 17,000 miles an hour, 25,000 kilometers an hour. Orbital speed, kinetic energy depends on the square mass and the square velocity. K equals 1/2 mv squared. So when you take 25,000 kilometers an hour and you square it, that's a hella big number. And when you're talking an impact like that, an object like this big would devastate the space station or any satellite. No satellite has armor that could withstand this. Any satellite weapon, a coffee can full of BBs with an M80 inside it, going anti-orbital. And you just pop and you get this cloud of BBs, your satellite flies through, you're done. Remarkably easy to
Don't give anybody any ideas.
Well, trust me, the people in dark secret rooms who plot these things for our national defense, I'm not giving them any. And the best thing is I can talk about fireworks like this and nobody can go build one in their backyard.
Right.
If they can do that, somebody's going to figure it out. Elon Musk, I'm looking at you. But we talk about satellite being artificial. Moons are not. Moon and Moonlit is defined by gravitational processes, which is appropriate because the relationship of moon to a planet is defined by gravitational processes. And the shape of the orbit is controlled by gravitational processes. You see where we're going here, Scott? Our entire definition of moon, moonlit, and orbit all go back to first principles of gravitation. So Isaac Newton, Albert Einstein, the two of them, and this is probably more Newtonian than Einsteinian, although we did our nifty little, here's our that's little, right. Yeah. That's my model for today, clay model of a gravitational gravity well. But essentially, we define moons by gravitational means. Gravity decides. We don't have to. And if we want to put adjectives in front, like the sign at Disneyland, which says you must be this tall to ride the roller coaster. If you want to say, oh, if you're smaller than this big, you're a dwarf planet, I have no problem with that. Just stop saying it's not a planet. Now, when it's no longer able to be a sphere, clearly it's not a planet, it's something else. It's an asteroid. Fine. But, it's the old Tolkien thing. One ring to rule them all, one ring to find them, one ring to bring them all, and in the darkness bind them. Certainly gravity fits the description of the one ring. It finds them, it brings them, and in the darkness binds them. Once a moon is bound inside a planet's gravitational well, then it's a moon. If it escapes via the Roche process and tidal dynamics, guess what? It's not a moon anymore. If our moon, someday it will slip the bonds of Earth's gravitation. Once it becomes independent, it's a planet. Until it comes back to the Earth's gravitational field, which the boffins who run the computer simulations say that happens within a millennia. And usually it's a re-impact sort of reacquaintance, which will be bad. But I won't be here, so,
You're good.
Yeah. But, and planets like Jupiter and Saturn, the great gravitational magnets that they are, they acquire and lose moons all the time. They are like 3-year-olds with Happy Meals, with Happy Meal toys. They always want another one. They broke the last one they had, or they've lost it. I've lost it, I've broken, ooh, shiny, I want another one. Jupiter's always acquiring asteroids, capturing them, moonlit, fine. It's losing them, asteroid. And the status depends not on the object, it's a status that depends on a relationship, a gravitational relationship between a planet and a chunk of metal, stone, or ice floating through the darkness. There you go. I would love to hear comments from our
Okay.
audience.
All right. All right. So let's pick some here. We have we'll recognize our group on let's see. You got a thank you from Beatrice Hines on providing the study guide.
Hey,
Yeah, and some people want to know if there's actually going to be a test or something.
no.
You can save that for another time.
Writing tests is actually one of the more bothersome things about teaching.
Yes.
But you can test me. You can send me your quiz questions at astronomyforeducators@gmail.com, and I will endeavor to take your quiz.
Let me read through this. Beatrice Hines, Chris Larson, Book Davies is on, James the astrophotographer. Beatrice is saying hello to everybody. Cameron Gillis is watching.
There's many questions this week. We had quite a few.
Let's see, going through it, a lot of salutations here. Something about that's where the Planet X theory came from.
Oh yeah, Planet X. And there's been a variety of things. Vulcan, of course, was the planet on the opposite side of the sun from us. And we disproved that one. We thought Vulcan was disturbing the orbit of Mercury.
Oh, really? Huh.
Yes.
Okay.
And Einstein, of course, proved that Mercury was disturbed by the sun's bending and warping of space-time. Vulcan wasn't required. Occam's razor wins again. The simplest, although people say relativity is complex, you know what? It was the simplest explanation. The sun plays with the gravity field around it, and that controls Mercury's orbit. It doesn't require another planet.
There's a comment of there's a name or a word for almost everything. It's true.
Yeah. But science, again, is about very precise definitions based upon truly scientific principles. In other words, principles based on data, observation, verifiable. And when we make moon a term of relationship between a planet and an object that is controlled by gravitation, we take it back to one of the 4 or maybe 5 fundamental forces of the universe. People argue whether or not dark energy is a 5th force. But certainly, gravitation is one of the handful of fundamental forces that controls our cosmos. I like to say in my astronomy program that gravitation is the fountainhead of all creation. And when we define moon as a relationship controlled by gravity, it becomes very precise and very easy. Occam wins, Copernicus wins, Kepler loses, but oh well.
Kepler loses.
Yeah.
Martin Eastburn made a comment. So nuts and bolts floating in space are satellites? Question mark.
Yes, certainly they are. They perhaps, they are no longer in a controlled orbit, but they are certainly man-made artificial objects confined within the gravitational field of the planet. And anybody who invents the space Hoover that will clean up that mess will be very wealthy indeed.
Right.
That's one of the things from the original Star Trek program. They had that big deflector dish on the front of the Enterprise. That was for catching debris and pushing it out of the way, because at relativistic speeds, impacting a dust grain would be like a thermonuclear bomb.
Be like vaporized. Yeah.
Yeah. So they had that deflector dish. And the Earth has its own deflector dish. It's called the magnetic field.
Right.
We deflect a lot of the harmful solar radiation that way. So it's not a, but Roddenberry was pretty cool futurist in my book. Stuff like that. I'm like, wow, awesome.
There's a comment that says Pluto is a dwarf planet. Mercury, Earth, and Mars are terrestrial planets. Jupiter and Saturn are gas giant planets. Uranus and Neptune are ice giant planets.
Certainly. And all those adjectives are relevant. None of them remove the status of planet.
True.
If Earth is a terrestrial planet, are non-terrestrial things not a planet? Well, that doesn't seem right. That's a temporary and coincidental property. Your gravitational shape as a sphere is not. That's a fundamental property. What you're made of, stone, ice, whether or not you have an atmosphere, are you primarily liquid or solid?
Jeff Wise comments, he says, these explanations and definitions are very helpful, Dr. Barth. Thank you.
If anyone at the IAU is listening, you're welcome to adopt these helpful definitions.
That's right.
Well,
That's right.
People say, well, who are you to make a definition like that?
That's right.
Hello.
Armando Lee, I think Armando's in the Philippines. He says the IAU apparently gave premium to not only whether an object is a planet is captured by a planet gravity or not, but also its shape, presence of, and this is presence of other objects in its orbit the sun, or in its orbit around the sun. Don't quite make up that sentence, but
yeah, it's interesting. And I saw somebody did a calculation on this, and I've never rerun the simulation. I don't have that kind of computer power, but they said if you took a planet the size of Jupiter,
yeah,
and you put it in a distant orbit, say Pluto was the one they originally picked, but certainly the argument goes for more distant orbits. If you put it in a more distant orbit, say at 100 AU, Jupiter is absolutely a planet. The age of the universe isn't great enough yet, being that far out, it would go so slowly and have such a large torus of volume to clear. It couldn't have cleared its orbit and become a planet yet. I'm reminded of the story of Pinocchio and the Blue Fairy. I want to be a real boy. And had to, it's a classic hero story. You must accomplish certain things, young Jedi, to become a true Jedi. And so Jupiter at 100 AU, the universe isn't old enough yet for it to have cleared its orbit of all the debris and Kuiper Belt junk that's out there. It couldn't have done it yet. So is it not a planet? It just, the definition falls apart on so many levels.
I think there's some discrimination going on here.
Well, dwarf is certainly a reasonable adjective, and it's reasonable to have classification systems.
It's small.
Certainly. Right. And it's reasonable to say, oh, we have dwarf planets and we have giant planets, right?
Giant planets, right?
We have giant planets. We have Earth-sized,
Like somehow that's normal.
That's right. And we have dwarf planets. I'm okay with that. If you're this small, you're a dwarf. If you're this big, you're just a regular vanilla planet. And if you're this big, you're a giant. I don't know if it's very nice to call someone a giant or a dwarf.
That's that centric thinking going on again, right?
Right.
That somehow we're the center of the universe. It is
the very exemplar of the Copernican fallacy.
Right.
That's
Davey says, I don't think there's an official name for this, for the moon. Moon comes from Old English mona. Luna is Latin. Selena, I think, was the Greek.
The name is French, yes. And the names amongst different cultures and languages of the earth are legion. And moon and month have the same root. So I've always, when students said, well, if there's lots of moons, why is ours just called moon? We don't have lots of Earths, we have planets, and ours is called Earth. They said, well, then call it Luna. Science often adopts Latin nomenclature. So
yeah, that's a nice one.
Luna.
I like Luna.
I use that in my science classes. I referred to Luna. And a moon was a generic object in relationship with a planet. But I referred to our moon as Luna and our star as Sol. And, that's not unreasonable Latin-based scientific terminology. It's an old. You'll forgive me, Scott. It's an old Star Trek joke. One Klingon says to the other, "Well, what kind of species would call their home planet dirt?" And I'm like, yeah, okay.
Humans.
Yeah, humans. What other species would call their home planet dirt?
That's right.
So Earth. And we have all these cultural biases because astronomy is the grande dame of the sciences. It is ancient. It is venerable. It has been around for millennia uncounted certainly before written, probably before language. The idea of astronomy almost certainly predates formal language.
Oh, sure.
And so how ancient is that? So surprise, some of our definitions and terms need to be updated.
Yes.
But again, I think go back to first principles. The idea of units in physics, you know this. Units in physics are all based on meter, kilogram, second, right? The MKS system. They're all defined by the meter, the kilogram, and the second. A Newton of force is a kilogram meter per second squared. And so we have this tradition in science. Let's make all our units based upon fundamental measurements of basically mass, length, and time. Well, shouldn't our scientific definitions like moon and planet tie back to first principles like gravitation, strong force, weak force, electromagnetic force, etc.? And the one ring that in the darkness binds them is gravity. Really, it is. Tolkien could have just been describing the gravitational force. One that gathers them all, rules them all, and in the darkness binds them. Gravitation, how else is a black hole defined except by gravitational first principles? How is a neutron star defined except by gravitational first principles, right? Degenerate matter of a white dwarf, what's it defined by? Gravitational first principles. Right. Remember the fight between Chandrasekhar and Eddington? Eddington brought Chandrasekhar from India, gave him this scholarship, and on the boat, on the way, Chandrasekhar in paper and pencil works out the idea of the white dwarf and degenerate matter. When you add more mass to it, it becomes more compressed.
Okay.
Eddington hated it. Wouldn't support Chandrasekhar's PhD. He had to go to a different university to get his PhD. He did eventually get a Nobel Prize for degenerate matter and white dwarfs, but it was after Eddington was dead and could no longer lobby against him.
Jeez.
He waited almost 60 years for his Nobel. I think he waited longer than anybody from his fundamental research, which was actually done.
You have to be living to get the Nobel, right?
You have to be living.
Wow.
And I think there are times when we turn our back and we recognize something only in retrospect. I think Gilbert Levin's discovery of microbes on Mars will be in that category. Is it proven yet? No. Boots on the ground. Can I prove it? No. Do I believe it's true? Yes. That's the difference. That's me as a scientist. I know things I believe and things I can prove, and I know the difference.
Right.
But there's things that suggest themselves to me as eminently reasonable. I get asked all the time, do you believe that there are aliens out in space? And well, I kind of twist the question subtly. Do I believe there's other life in the universe? Absolutely. Something like 100 billion planets in our galaxy and maybe 1 trillion galaxies? Yes, of course. Statistically, the idea that this is the one place with life on it is just ridiculous.
Right.
It doesn't meet Occam's razor. It doesn't meet Aristotle's improbable possible. The statistic improbability that we are alone just is dwarfing. Can anybody prove this? No, not yet. But when I was in school, I was told by a teacher, there is no other solar system but this that has planets on it. I was taught that. It was in my textbook.
Yeah.
Next week, Scott, we're going to take on our 5th program in our Dynamic Moon series, we're going to take on the origin of the moon.
Okay.
And I'm sure a lot of people are going to say, well, gee, Dr. Barth, why are you leaving the origin till last? Did you ever read a comic book? You never get to learn about the origin of Spider-Man until you're
The prequel, right?
Prequel, right. And it is one of the most fundamental mysteries. And it's one of the wonderful, wonderful things that came out of the Apollo program. And it explains so much about our solar system. So next week, friends, we're going to take on the origin of the moon. And yes, I will once again bring in some of my wonderful clay models and some of my top deck drawn on Microsoft Paint illustrations. And we'll have good conversation and fun. So I hope everybody will see us next time. And please download those study guides. I'd love to hear your comments, astronomyforeducators@gmail.com. And much of this is based on the Astronomy for Educators text. The link is there on Scott's page. I hope that you will download it, peruse it, share it with your friends who are teaching, because they need the resource.
That's right. That's right. Yeah, Armando Lee had a interesting comment about define life first. Our definition, in my honest opinion, is again Earth-centered. So, yeah, what else do we got? You know, so
anti-entropic, self-replicating processes.
Right. Book Davy says, I'm going to read out before these programs, as long as I know the subject beforehand. Sure. Gary Albin, tardigrades on Earth. Who knows what else is alive and thriving on other planets? We have so much to learn.
Absolutely.
Yeah.
Well, there are people who have questions that maybe, was the Viking lander sterilized well enough? Are there microbes on Mars that are invaders from Earth? Maybe. Martian meteorites, give rise to the question: gee, are there organisms on Earth that are invaders from Mars? Are we all really Martians? Everybody's from somewhere else. If you go far back and up in the family tree, is the old adage of genealogy, I suppose. Maybe it's true cosmically as well. So I'll look forward to seeing all our viewers next week. Please download the guides. Scott puts them up usually a day or so in advance. And I'd love your questions. I'd love your questions. Chat room, email, we'll tackle them all. Thank you, everybody.
Dr. Barth, thank you very much. And don't forget, tomorrow we have the Open Go-To community with Jerry Hubble, and we have the 52nd Global Star Party with a special guest is Davis Sobel, who wrote Longitude and Galileo's Daughter, and a number of other great scientific books. So you'll want to catch that. And until that time, you guys keep looking up. And thank you.
Clear skies, everybody. Bye-bye now.
Hello, everybody. This is Scott Roberts from Explore Scientific. And today I want to talk about the world-famous Galileo Telescope Kit. This is a kit that you assemble by yourself. You'll learn how optics work by assembling the objective lens and also the eyepiece. And there's two different eyepieces that are in this. It's a 25 power, 20 millimeter eyepiece, but it also comes with this very clever little device here that works both as a Barlow lens that will double the magnification of this eyepiece, making it 50 power, or it can be used also as a Galilean eyepiece, which gives 17 power to the telescope. This is what Galileo virtually saw through his own telescope. So you can have that same experience that Galileo had looking at the moon, looking at Saturn's rings, looking at Jupiter. It is a telescope that was designed for the International Year of Astronomy in 2009. And it's a fantastic kit, both for child and adult, to learn how a telescope works. And so if you get the telescope like this, you can either have it on a stand like this, you can hand hold it like a pirate's glass, or on the bottom here, we have a threaded hole here that you could put it on a camera tripod. Very versatile, very rugged, and a lot of fun, all from Explore Scientific.